Hi, I'm Jixing Tang. Today I'm going to talk about microstructural characterization of ultra-thin polycrystalline silicon films using CEA approach, standing for CMP, Etching, and AFM. On this slide, I would like to explain why we focus on ultra-thin polysilicon films and why CEA approach is needed. First, in the ultra-thin regime, conventional crystallography techniques becomes unreliable. Methods like EBSD or TEM8 typically require polysilicon film thickness on the order of hundreds of nanometers. It strongly motivated the development of alternative microstructure-sensitive approaches. In addition, this thickness range is highly relevant to scaled device structures and advanced polysilicon applications. While EBSD-based techniques require relatively thick films and can cause irreversible damage, the CEA workflow is non-destructive at the microstructural level and remains sensitive to crystallography orientation and defects. Importantly, by using CMP to precisely control film thickness, this approach enables microstructural characterization down to 13 nanometers. Here is the outline of today's presentation. I'll first briefly introduce stir etching. Then I'll discuss two different approaches to analyze etching behavior. The first is a 3-sample ABC ranking method, which attempts to infer orientation-dependent etching rates from relative height differences. However, it turns out to be unreliable. Next, I'll focus on a single-sample same-area methods, which uses artificial scratches as markers to relocate the same 3x3 micrometer region during sequential etching. Using AFM, this approach allows us to track microstructural evolution during stir etching and reveals an orientation-dependent tendency to accumulate defects and residual strain. Finally, I'll summarize the key findings and conclusions. On these slides, I briefly introduce the physical and chemical basis of stir defect etching. First, different crystallography orientations can exhibit different etching rates. Beyond orientation effects, microstructural defects further enhance local chemical reactivity. This makes defect-rich regions the preferential etching sites compared to the defect-free crystalline areas. As a result, defect etching can selectively reveal microstructural heterogeneity in polysilicon. On the chemical side, stir etching solution consists of chromium trioxide and hydrofluoric acid diluted in DI water. The etching mechanism involves two coupled steps. First, silicon is oxidized by chromium trioxide, forming a thin silicon oxide layer, and then this oxide is selectively dissolved by hydrofluoric acid, exposing the underlying silicon surface. Because both oxide and oxide dissolution proceed more rapidly at defect-rich sites, the resulting etching behavior is highly non-uniform and microstructure dependent. Here I first introduced the 3-sample ABC ranking method, which was the initial attempt to extract orientation-dependent etching sites. The basic idea is to assume that different grain orientations etch at different rates, which leads to height differences between grain plateaus after etching. If we check the same relative height differences after an additional etching time delta t, we can write the height evolution in terms of etching rate r, time t, and height z. Under this assumption, the relative height change between the two grains should scale linearly with etching time. Initially, this approach appears self-consistent and seems to provide a way to rank grain orientations by their etching rates. However, as I will show in the next slides, this method breaks down experimentally, mainly due to sample-to-sample variations, and the fact that relative height does not uniquely represent identical crystallography orientations across different samples. This slide shows AFM height image of a 30-nanometer polysilicon film after 20 seconds stir etching. We can already see distinct bright and dark grain plateau, indicating significant height differences introduced by etching. To systematically analyze these differences, I manually mapped the grain structure on the right and classified grains into 3 categories based on their relative height. A grains correspond to the highest plateaus. B grains to intermediate heights and C grains to the lowest plateau. At this stage, the classification is purely height-based. The implicit assumption is that grains within the same height category represent similar crystallography orientations, or at least similar etching behaviors. Rather than comparing only individual grains, I adopted a pairing strategy to improve statistical robustness. For each A grain, I pair it with multiple B grains to form an A to B dataset. The same approach was used for A to C and B to C comparisons. This generates multiple height difference values for each category, allowing us to calculate an average height difference and standard deviation. If the ABC ranking method is valid, these averaged height differences should consistently reflect intrinsic orientation-dependent etching tendencies. Here I summarize the quantitative results for the 20-second etched sample. After averaging over all pairings, the height differences are approximately A to B, it's 7.1 plus and minus 0.5 nanometers. A to C, it's 11.1 plus and minus 0.7 nanometers. And B to C is 3.9 plus and minus 0.4 nanometers. These results appear internally consistent. A to C shows the largest height differences, B to C the smallest, which matches the expected ordering based on the relative etching rates. At this point, the method appears to work reasonably well, motivating the next step, testing the reproducibility using a second sample with a longer etching time. In the next step, I apply the same ABC ranking method to a different 30-nanometer polysilicon sample, etched for 25 seconds. Here, an important assumption is implicitly made that the ABC in this 25-second sample has the similar crystallography orientations correspondingly to those in the 20-second sample. Also, using the same pairing strategies, I performed the A to C, A to B, and B to C comparisons for the 25-second etched samples to generate statistically meaningful height difference distributions. This allows a direct comparison between 25 seconds and 20 seconds databases. The average height difference for the 25-second samples are shown to be A to B, it's 8.0 plus and minus 1.1 nanometers. A to C, it's 11.1 plus and minus 0.9 nanometers, and B to C, it's 3.1 plus and minus 0.4 nanometers. At first glance, these values appear reasonable and similar to the 20-second results. However, when comparing the two etching times, certain trends do not evolve consistently with increasing etching time, which raises concerns about the validity of the methods. This slide summarizes why the three-sample ABC ranking methods failed. First, the 20-second and 25-second measurements were performed on different samples, even though they had the same nominal thickness. Sample-to-sample variations, such as grain distribution, defect density, introduce uncontrolled differences that obscure true etch rate effects. Second, and more fundamentally, the ABC categories are defined purely by relative height. There is no guarantee that an A grain in one sample corresponds to the same crystallography orientation as an A grain in another sample. As a result, cross-sample comparisons based on ABC ranking do not reliably reflect orientation-dependent etching rates. This failure directly motivated the development of the second SAM methods, where the same ultra-thin sample and the same local area are tracked across multiple etching steps, eliminating sample-to-sample ambiguity. To overcome the limitation of the multi-sample comparison, we developed a single-sample, same-area tracking method inspired by Chaya. The key idea here is to etch the same ultra-thin polysilicon sample multiple times, while repeatedly imaging exactly the same surface region by AFM. To achieve this, I first introduced artificial scratches on a thin film surface. These scratches act as permanent markers that are visible under optical microscopy and AFM. The workflow is summarized on the right. First, artificial scratches are made on the film. Then, the target area is located using AFM with reference to these scratches. And then, a core scan is performed over a 10 by 10 micrometer area to ensure correct positioning, followed by a high-resolution scan taken over a 3 by 3 micrometer square region. Finally, the same procedure is repeated after additional third etching steps. This approach allows us to track the same grains across different etching times, eliminating sample-to-sample variation and orientation ambiguity. This slide shows the starting point at 3 seconds, etching for the 13 nanometer film. I begin by navigating a region close to the scratch marker and performing a 10 by 10 micrometer overview scan. From this overview, I select a specific 3 by 3 micrometer area shown by the white box and take a high-resolution scan. This 3 by 3 region is chosen as the reference area, and it will be used as the target for all sequential etching steps. This slide shows the same sample after increasing the stir etching time to 8 seconds. I first return to the scratch marker and perform another 10 by 10 micrometer overview scan in the same reference region. Within this overview scan, I then search for the same grain configuration that were observed in the 3-second sample. By matching distinctive grain shapes and relative grain positions, I am able to relocate the original 3 by 3 area. Once the same region is identified, I take a resolution high-resolution scan. Again, I follow the same procedure. I start from the scratch marker, perform a 10 by 10 overview scan, and use the grain morphology as the fingerprint to identify the previously defined 3 by 3 area. Despite the increased etching time and stronger topographic contrast, the overall grain geometry remains recognizable as the larger scan scale. This allows the same 3 by 3 region to be reliably relocated and rescanned at high resolution. This slide shows the same 3 by 3 area tracked across 3 different stir etching times, 3 seconds, 8 seconds, and 12 seconds, for the 13 nanometer polycrystalline silicon film. Because this is exactly the same region, any change we observe here is purely due to additional etching, rather than spatial variation across different samples. As the etching time increases, the contrast between different grains becomes progressively stronger. At 3 seconds, the surface is relatively smooth with weak height contrast. At 8 seconds, grain boundaries and internal features start to become clearer. By 12 seconds, some regions become significantly brighter and rougher, indicating much stronger local etching. This same area comparison provides the foundation for the following quantitative analysis, where I examine how different microstructural features respond differently to stir etching. On this slide, I focus on the representative grain boundary within the same tracked region. On the left is the AFM image at 3, 8, and 12 seconds, marked by the arrow of the grain boundary. On the right, I plot the corresponding height profiles extracted along the same line for all 3 etching times. At 3 seconds, the grain boundary shows only a shallow height depression. As the etching time increases, a clear and deep groove gradually develops at the grain boundary. This behavior indicates that the grain boundary etch faster than the grain interiors, which is consistent with the presence of the higher defect density and local strain at grain boundaries. Next, I examine an orientation boundary within a single grain, where 2 regions have different crystallography orientations. Compared with the grain boundary case, the evolution here is more gradual. Instead of forming a deep, localized trench, this boundary mainly develops as a step-like height difference between the 2 sides. This indicates that the contrast as the orientation boundary is dominated by the orientation-dependent plateau etching. One orientation is removed faster than the other, whereas the much deeper groove at grain boundary is driven primarily by defect-enhanced etching as the grain boundary itself. In this slide, I focus on a representative twinning section within the same tract region. At 3 seconds, the twin-related feature is relatively subtle, and the height variation across the twin is small. As the etching time increases, the height contrast associated with the twin becomes much more pronounced. One explanation is that the etching rate of the twin plane itself is relatively low compared to the surrounding grain orientations. In addition to becoming taller, the twin-related feature also becomes narrower and steeper with increasing etching time. One possible explanation is that the etching is not uniform across the neighbor of the twin. The material adjacent to the twin plane is removed faster than the center of the twinning, so the sides retreat where the core remains. In this slide, I look at the surface evolution along the twinning line within the same tract region. As the etching time increases, the profile becomes progressively rougher. The fluctuation becomes larger and more frequent, especially by the 12 seconds. A plausible explanation is that the twin-related region is not chemically or structurally uniform as the nanoscale. Even though it looks like one line in the image, it can contain a high density of local defect sites, or subtle structural irregularity distributed along the twin plane. Under stir etching, these sites do not etch at exactly the same rate, so as etching proceeds, small differences in local reactivity accumulate over time, and the result is a more uneven topography along the same line. In this slide, I want to explain why it is difficult to extract the etching rates from this sample, even though we are tracking the exact same region. At the top, it's the same tracked AFM area after 3, 8, and 12 seconds of stir etching. Visually, we can already see that the surface evolution is not uniform. Some area remains relatively smooth, while the other areas become much rougher as etching time increases. The first key observation is that the grain plateau roughness increases strongly with increasing etching time. This means that grain interior is not behaving like a flat reference plane that is etched down uniformly. If the plateau itself is evolving and roughening, then using the average height of the grain interior to estimate thickness removal is unreliable. Also, the second observation is that the brightest regions show strongly non-uniform etching behavior. These high contrast areas do not change in a simple linear way with time. Instead, they develop high local peaks and roughness much faster than the surrounding regions. One possible explanation is that these brightest regions may contain more microstructural defects, or another possibility is that they may carry higher residual strain introduced by excimer laser annealing. Either way, both effects will locally accelerate the chemical reaction and create strong spatial variation in etching response. To summarize, in this work, it's demonstrated that the CEA approach, combining CMP, defect etching, and AFM, provides an effective way to characterize microstructural features in ultra-thin polysilicon films down to 13 nanometers. By applying stir defect etching, we were able to clearly reveal microstructural heterogeneity. Grain boundaries, orientation boundaries, and twinning-related features all show distinct and time-dependent etching behaviors. Importantly, it showed that the 3-sample ABC ranking method fails for this system due to strong sample-to-sample variation. Instead, the single-sample, same-area tracking approach enables a much more reliable comparison of etching evolution over time, because it eliminates ambiguity caused by the spatial heterogeneity across different samples. From the tracked region analysis, we observed that the orientation-dependent etching behavior is not governed solely by the crystallography orientations. Local defects and residual strain introduced by ELA play a critical role in modifying the effective etching response. Finally, as discussed in the previous slide, the strong increase in grain plateau roughness and the highly non-uniform response of the brightest regions make it difficult to apply the same etching rate extraction method used previously. Overall, this work demonstrates that the CEA methods provides a robust and effective characterization framework for ultra-thin polysilicon films down to 13 nanometers, offering a clear advantage over traditional approaches by enabling reliable same area analysis at thicknesses where conventional techniques becomes ineffective. Thank you.